this by one level, it already gets quite lengthy. It's not more understanding. If you understood the 4 cycle, you also understood the 6 cycle. So this could be one exam task related to this LTPC codes. Okay, so we could identify our 4 cycle in this way. And this is actually where we want to proceed today. So we can also identify these cycles in the parity check matrix. So this is also interesting. Let's see, identify cycles in the parity check matrix. We come back to our example that we know already. I want to use again the Hamming code as example, because typically you would use larger matrices here for the LTPC codes. This was looking like this. Followed by the identity matrix here. And maybe it would be good, just for illustration purpose, to have a look in parallel again at the 10. So let's note this here. We basically see our check nodes. Here, see our bit nodes, basically. Check nodes. Bit nodes. So the first bit node connected to check node connected to the first 3 guys. To use a different color, illustrate this again for you. Obviously, so first 3 bit nodes being connected to check node 1. And also the 5th one. This is basically, again, how this parity check matrix, basically describing our parity check equations, translates into this Tenor graph. So for the second check node, we use second guy, third guy, sixth one, and for the last one, we use the first, second, and the last one. Check nodes, bit nodes. Now let's look at this cycle we found. cycle over this guy here. This one. Oh, wait. Cycle, basically. See the cycle, it's actually going down the second one, then up to the third one, back to this guy. Red, we have this cycle. For path here. Back again, origin. Yeah. So let's see basically how this looks like in the parity check matrix. So the transition between bit node 1 and check node 1 is this one. Then the transition between check node 1 and bit node 2 is this one. Check node 1, bit node 2. Oh, wait. Wait. This one here. So bit node 2, check node 1 is this one here. Then between bit node 1 and check node 3, it's this one. And between bit node 2 and check node 3, it's this one. Yes. So let's look at this one. This basically describes that bit node 1 is used in check node 1. Action. Describe this one later on. Action between B1 and C1. So bit node 1 is used in check node 1. Basically this guy. The second one, bit node 2, is also connected with check node 1. Action between bit node 2 and check node 1. It's this one. This one, bit node 1 connected with check node 1, bit node 2 connected with check node 1. Down here, we have bit node 1, so first column of this matrix, third row. So bit node 1 is also connected with check node 3. This one here. Action. B1, C3. And finally, this one here, well, this is straightforward. This is B2, c3. Basically, this matrix H describes the edges of this graph. So where do we have connections? We can see this in our parity check matrix. And now we basically see how this is working. If we have one entries in our parity check matrix being aligned like this will always turn into a cycle. From bit node 1, bit node 2, check node 1 over bit node 2, check node 1 being linked to check node 3, bit node 2, and so on. So this square arrangement of one values will basically lead to such a cycle in the tenor. Let's note this, and then we look at another example. Square arrangement of ones in the tenor graph will yield a 4 cycle. And we already know 4 cycles are bad for the performance. We'll use information, try to avoid. Yes? Wait, I didn't understand. Could you speak a bit louder? Ah, okay, yes, of course, it's not the tenor graph, it's the square arrangement in the parity check matrix, of course, yes. Thank you. Check matrix. Yes. So here's again the question or the statement that, of course, the parity check matrix is directly linked to the tenor. One results out of the other. It's just an illustration check matrix. So will we have another 4 cycle or 7,4? See it at the matrix, or you can see it in the tenor graph, but probably it's even more easy to identify in the matrix. It's 4 guys here. Even would have one more here. So we have a couple of 4 cycles here. So this one cycle, you can also try to follow this on the tenor graph. So obviously also over check node 2, bit node 2, check node 2 goes also to bit node 4, check node 2, bit node, this guy, check node 2, bit node 4. Well, and then you see up check node 3 down to bit node 2. Also here we have another 4 cycle. Actually identify these 4 cycles in the parity check matrix, or the other way around. If we would like to come up with parity check matrix having a good performance, we need to make sure that this arrangement of ones in a square will not appear. So we could try to modify this parity check matrix now such that the cycles disappear. So for example, if I use the 0 instead of the 1 here, I could break up this first 4 cycle, and maybe using a 0 here instead of the 1, I would break up the other 4 cycle. So this will be important if we think about how smart parity check matrices could be constructed to get a good parity checker. Yes, this is actually. Yes. Yes, so actually also for the online students here, one student noticed that this could be the reason why good parity check code matrices have sparse characteristics, so containing only few ones. And then of course, if we have only few ones, it's more and more unlikely that we will get like the 4 ones in a square. So this is one reason. This is one reason. Why sparse matrices parity check matrices more cycles will be unlikely. Want to come up actually with another definition here. It's the so-called girth of a code. Basically describes the length of the shortest cycle appearing in this kind of check matrix. Girth code is length, its shortest here. Shortest cycle we can have is of length 4. Girth So this is one reason why our 7,4 Hamming code will not be very good LDPC code. Will be limited in performance due to these 4 cycles that appear here, obviously. So not a very good parity check matrix here that we've chosen. Sorry, I didn't get the beginning. Okay, so here the question is again, what's the girth, this code? Well, the girth, this code basically is just giving us a hint how powerful this code is. If you have a code with a low girth, you notice we have the problem with the short cycles. If the girth would be 6 or 8, it would be better because this means we don't have shorter cycles. So if we had girth 6, we know the shortest cycle that appears is of length 6. We can have at least 2 iterations where we benefit from completely independent information. Just after the 3rd iteration, I start reusing what is already there. If we had a girth of 8, we would have 3 iterations generating independent information. Just after the 4th one, I would reuse existing stuff. So a code with a larger girth will have the better performance. So typically, I think codes with girth of 8 are used. So this would be a typical. Yes, it's a property of one specific code being used. For example, we could see codes being used in 5G. I think typically they have a girth of 8. So there we have matrices that avoid these short cycles. This would be like a design goal when designing good parity check matrices, avoid the short cycles. Trying to get a large girth. Okay. Let's see. So let me switch over the lecture slides here. So here I summarized this again, also referring to some papers where you could have a closer look at this. So when the girth is smaller than 6, the bit error rate is significantly higher as if we did just some maximum likelihood decoding. Well, here you could ask why we just don't do maximum likelihood decoding. It's just due to the computational complexity. So if we have large code words, we really would have to calculate many Euclidean distances, which is computationally just not feasible. We need to come up with some smarter decoding algorithms. Decoding on the Tanner graph with this feeding back and forward is one method to do this more efficiently. So we want, in any case, a girth being 6 or larger. Then also one result here figured out by these researchers is that if we have Tanner graphs without any cycles, we will only get a small minimum Hamming distance. So actually I don't have an example illustrating this, but you could imagine if we had a parity check matrix with only very few ones. Of course, also the resulting code words will be different in not so many positions. So if we make our matrix more and more sparse, also our code will tend to show a smaller minimum Hamming distance. So meaning the resulting code words look more and more similar. That's also what we would like to avoid. So this is why good codes are somewhere in between. So as I said, so a girth of 8 would be somehow typical. Okay, let's see. And also here I referenced the paper, so you can download those papers. Okay, and then basically here we example with this. So we already have this. Questions. Otherwise, we would start to have these are done in G. This will be again difficult story. Yes, so here the student had a question that the LDPC codes are slightly better as the turbo codes. And what's the reason for this? So actually, there will be several reasons. So maybe we see this more clear when we have a look at how things are done in 5G. So one reason is if we find good parity check matrices, the implementation is very efficient. We can have like parallel processing of several check nodes. So we can use basically the same hardware structure to compute efficiently these log likelihood ratios. So the implementation will be more efficient as if we look at the turbo codes. And I think that's already the main reason. And it's also more easy to process larger parity check matrices, where basically the computational complexity for the turbo codes will like explode. So it will be hard to get the computations done for the turbo codes. So the main reason using the LDPC codes is also their computational efficiency. So they can be implemented easily, efficiently, and with very low computational power, we can actually decode those. So there we are again at the point where we would have to discuss about how many joules are needed to decode a single bit. And there the LDPC codes will be way superior as compared to the. So I think this is the main reason. So also for the turbo codes, if I do many iterations, I will get similar good results or as good results as for the LDPC code, but it's more complex. Okay, let's have a closer look at 5G, what's used in 5G. Let's also start here with the lecture slides. So let's see what we need to understand to get this done. We should know how these parity check matrices are defined, how they work, how the parity check equations are reflected in this parity check matrix. We should have understood how the decoding works, this iterative decoding between the check nodes and the bit nodes. And what always helps is a rough idea of the 3GPP standards. So that's the wireless standards mobile phones operate, basically. And what we want to learn here is basically how these LDPC codes are used in 5G systems, why certain parity check matrices are used there. So we can also not explain this in full detail because you see it will be quite complex, but you will get the idea why certain matrices are used. Okay, let's see. So we have some site constraints here, 5G system. So we want a low implementation complexity. This is what I mentioned already, because due to the limited computational power of our mobile devices. We want to save energy. I don't want to recharge my mobile phone every. So we want to be energy efficient. We want a low latency of the code. So this means actually I would like to do not like 100 iterations until I end up with the decoding result. I would like 3-4 iterations and then being done. Because otherwise, of course, I would introduce delays due to my decode. So I don't want many iterations. I want a fast decoding here. Yes, so here again, a student asked for the complexity. Student asked for the complexity of the encoding process. And well, this is one benefit of the LDPC codes. The encoding and the decoding can be implemented very efficiently. So we will see this when we look at the parity check matrix of the 5G system, how this can be used also to efficiently encode our bits. That's also a very good point. Also, the encoding is more difficult for the turbo codes. So another benefit that you discovered here, efficient encoding is possible. Okay, so, and one more benefit is, but this is due to the specific structure of the parity check matrices in 5G, that we can basically generate codes with variable code word length and variable code rate. So we are very flexible there. Whereas, for example, in 802.11n, so the wireless LAN standard, we basically just have 12 combinations how we could select block sizes and code rates. So there we are somehow limited. So for example, I cannot say, I want now for my transmission a block size of 100 bits and a code rate of 7/8, for example. Could be that this is not in the standard, so not possible, but maybe this would be the best choice for our current channel conditions. So I would like to be very flexible there when it comes to choosing a code word length and a certain code rate. Code rate you could also imagine as level of protection. So smaller code rate, like 1/5, 1/7, this means really many parity bits to protect my information bits. Whereas code rate towards 1, meaning only few parity bits for protection. So in wireless LAN, we have 12 combinations. In 5G, we actually have 1 bit granularity for the block size. So we can basically choose arbitrary length blocks, and we can basically use all possible code rates. So we gain in flexibility here, which means, of course, we can adapt our transmission scheme better to our current channel conditions. So for example, if you move from outside to the basement, of course, the channel will be worse. You will face a lower received energy per bit, a worse signal to noise ratio. So your transmission scheme should adapt to these bad conditions, maybe by transmitting more parity bits, so reducing the code, or also reducing the block length. This could be methods to react on degradation of the channel conditions. So, yes, so here's the question about the 1-bit granularity. So this means we can have a code word length of 731 bits or 732 bits. So I can basically arbitrarily adjust the length of the code. And for example, in 5G, so I'm not so much an expert of the higher layers in 5G, but we have certain different channels. So we have, for example, channels to transmit the data, where we transmit large code words, large blocks of data. We have also channels where we transmit signaling information, like telling the base station, I'm in your cell currently. So the signaling information is typically transmitted in short blocks. So we have different data and communication channels being standardized in 5G, where we have different requirements related to the block length that we are actually transmitting in these channels. Like data channels, large blocks, maybe not so strong protected by parity bits, whereas for signaling channels like important information, short block length with a strong protection. So I also want the base station to know that I'm in the current cell, even if I have really bad channel conditions, for example, in the basement. So I still will be able to signal with my base station, but maybe I don't have internet connection anymore because my data blocks are just not protected strong enough and they get lost. So different levels of protections for different services. And with the 5G standard, we can really adjust this very fine, basically. That's one benefit. Okay. So let's see how this continues here. So already here, benefit over the wireless LAN standard. So then let's see what is used in 5G. So also here I included a nice reference where in this paper you basically see a nice summary of the channel coding schemes, how they are used in 5G. It's because this goes a bit beyond what we will actually study in the lecture. So-called quasi-cyclic LDPC codes are used. We will actually see this when we look at the parity check matrix. And those are so-called protograph codes. So frankly spoken, this is we generate our parity check matrix from one specific graph, specifically structured matrix that is somehow repeated. A certain pattern make up a good parity check matrix, and this repetition of this submatrix basically will result again in a very efficient code as we can parallelize the decoding procedure, as we have the same structure repeating in this matrix. So this has something to do with the implementation efficiency of the code. Okay, so then we will actually see how to get the tenor graph for such a so-called protograph code, attaching multiple copies. And actually we will see that these matrices that are somehow repeated in this parity check matrices are shifted identity matrices. Again, this has the advantage of being efficiently to decode. So mostly the structure of this 5G matrices will result from the constraint that we want to decode them efficiently. Okay, and here we have again enabled parallelism in encoding, and so very efficient. So let's actually see how this is working. So in the standard of the 5G system, you will find so-called base graphs. So those are the matrices that basically define how your parity check matrix will look like. There are two base graphs, and they are basically selected by the block size, so the number of bits in a code word, and by the desired code rate. For example, if I would transmit short code words, let's say here like 290 bits, with a code rate of 0.25, so 1/4. This means very strong code, many redundant bits here. We would select this base graph 2. We will see how this looks like. Whereas if we transmit really a lot of data, typical data traffic, so long blocks, long code words, and code rates going towards 1, we would use the base graph 1. So here we are in the region where we transmit large block code, large blocks, so typically high traffic channels, whereas here we have the short blocks, strong protected. We use this base graph 2. So just to illustrate you the meaning of this graph here, code rate, block size, and we select between. Here we will see what these space graphs are. So, and this is where things start to look a little bit difficult. So if you look at the 5G standard, so this is directly copied from the standard, you will actually see the definition of these two base graphs being defined by basically the rows and columns and certain entries in the rows and columns. So maybe let's at least write this down for one example, that you actually get the feeling this works. So how are the parity check matrices? Find in G. First of all, state so easy. We have some optimization goals, efficient, N decode, plus avoid short cycles. Plus being flexible in terms of block length and code rate. In terms block length, code rate. So in the standard, G standard, so-called graph are used. Parity check matrix. Is generated. Prototype. Shifted versions. Repeat. Somehow H. So-called base graphs basically describe where the submatrices appear. Base graph. This is like 5G specific, the 5G base graphs. Describe where the submatrices here and how often they are shifted. e.g. matrix, size 4. So this matrix will appear then somewhere in this parity check matrices, and where this will be defined by the space graph. And furthermore, the shifted versions so shifting it by one means just like shifting it by one column. So this means the first column will end up here. Second column here. Third column. And the fourth column will go to the front. By one. Then we have shifted by 2. First column there at position 3. This guy. This guy. Use a protograph matrix of size 4. Being the identity matrix, we can have 3 other shifted versions of this one. This will be the last column. So do you already see something which is smart about these matrices? Thinking just about what we did before. about the cycles. At least this submatrices don't contain 4 cycles. None of these matrices, we have like the arrangement of like 4 bits in a square. So already these submatrices don't contain 4 cycles, which is good. And again, talking about computational complexity, if we implemented this kind of matrices, we could use simply shifting operations for efficient implementation. So I'm not so much the implementation guy. We are actually more interested in the theory, but just to give you the reason why it's done like this. Implementation is efficient if we have this kind of shifted identity matrices. Okay, so let's see, what did we write here? Yes. Yes, yes. So here a student was asking or brought the statement that of course the submatrices don't have the 4 cycles, but depending on how we arrange them in the whole big parity check matrix, it could be that 4 cycles appear. Yes, this is true. And this brings us basically to the next question. How can we arrange the submatrices in a smart way? Maybe also with the goal avoiding that then 4 cycles will generate it. Okay. Ah, okay, now I understand. Yes, so there's also an interesting question from a student here. He was referring to the structure that we had before with the parity check matrix being P transpose, the parity matrix followed by the identity matrix. So maybe we go back again one step. Here, this typical structure, parity matrix transpose followed by the identity matrix, but we will actually see that we would not even need an identity matrix here. So we could have here also any combination of bits. Having the identity matrix here just makes it easy to determine the parity bits. So I've shown you this before. This line basically says bit 1 plus bit 2 plus bit 4 plus parity bit 3 should be 0, or parity bit 3 is bit 1 plus bit 2 plus bit 4. So from this, I could very easily get the encoding equation how to determine this parity bit. If I have here another one entry, it would be more difficult to do, but it could also appear in this form. So when we look at the parity check matrix, we are not restricted matrices having the identity matrix back there. I would just need to get the identity matrix here if I would like to come up with the generator matrix belonging to this parity check matrix. So from this form, I could easily give you the parity check matrix. It will be P, so the beginning matrix of this guy here, transpose, and yeah, in front of it, the identity matrix. So if you have this form, you could easily get the generator matrix and use it for encoding. Whereas if you have more ones here, so not the identity matrix, then you cannot get the parity check matrix, at least not easy. But in the LDPC codes, We usually do not work with the generator matrix. We do the encoding also based on the parity check matrix. So this is why we will see in 5G, we will have not the identity matrix here. It will look somehow different. Yes, because otherwise you are right, we would have to take care that in our structure it will somehow end with the identity matrix, but it's not important for our G codes. Okay. So let's look at the base graph. So the 5G base graph. Base graphs. Also C standard. So those standards are available on the 3GPP webpage. So if you search for corresponding document, let me give you the hint here. If you search for 3GPP, then TS is actually the document. Of course, the 5G standard contains really many parts. Now it goes to the higher layers. How is this defined? So in this 38.12, this is like physical layer stuff. Channel coding. Yeah, just look for the most recent version. Example, I took the 15.20 release 15. So the releases will count up. So maybe next year we will have release 16, but the document number will keep the same. So, and what do we find here? It's really a bit tricky and hard to understand. So let's just describe this in the same way as we will see it in the standard. H base graph. So we will have and column indices. J. Starting with 0, 1, and again columns and so on. So-called Bij, we will see what this means actually. We have a so-called set index. Going from 0 up to 7. And now we find there on the first look somehow strange values like 9, 174, 0, 72. Those are numbers that we will 17, 7, so on. Question is how to get H. Get parity check matrix from this. Let's do get a matrix zero entries where we have zeros in H base graph and ones where we have non-zero elements. H base graph. This means from this guy here, so what do we have? We have the first column, first row, so of course we need to look at a certain set index, to the set index right away. Let's just assume we use the 0 set index. We would have 0, column 0, or first row, first column. This means column J being 0, I 0, and here we have a non-zero element. So this means here we would need to include a 1. So 0 here. It's the 10th 0. Maybe includes column index 10. We will have here actually 2 0 entries. Zero. This means also here in our matrix we will get a 0. Actually, one. Let's include the 11th one as well. Actually, let me increase the size of the matrix a bit here. So this will be of size 46 rows and 61 columns. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . again, defined in the standard like this. And this table basically just describes which elements need to be replaced here by zeros or by ones in the first step. So we will end up with a matrix being of size 46 by 68 containing ones and zeros. Yes. This guy. So basically here it continues. For example, in row 17, we also have column indices like going up to 27. So basically here, not each column must contain values. So here only the non-zero values basically appear. Otherwise, like in a complete list, you would have here this, how many columns are used? Like 60 or 68 columns. So actually you could also have here like 68 rows for this column index, but most of them will be zero. So here only the column indices appear where we actually have entry in one of these several sets that can be used. So the set index just describe differently looking parity check matrices. Depending on the numbers here, the matrix will look slightly different. So we can also select one of these sets describing a different matrix. But let's consider just the set 0, where the matrix is simply defined by these values, looking at all columns and all possible. See, this continues here on rows 2, 3, 4, 17, 18. Like it's defined for all rows how the entries in this matrix look like. See? So here's the question about the rows and the columns. To somehow shift. Here we go. Yes, of course you are correct. Like the row index is always 0 in this case, so we are just working in the first row, and the column index is changing. Yes, I mixed this up. It's very good you paid attention, because it's going up this way. So we have the 0 here for I being 10, for j being 10. Yes, sorry that I mixed this up. Yes, so basically these numbers define in the first step a matrix containing ones and zeros, depending on if the values are here 0 or non-zero. This is the first step. Second. Values are replaced by a C matrix zero elements by a zero matrix for example, if we have a set C of 4, G, we have a 4 by 4 zero matrix. So now we basically blow up this matrix by this factor set C. See, each entry would be replaced now with a 4 by 4 matrix. This means we get 4 times as many columns and 4 times as many rows. And this is also called the so-called lifting size of the matrix. So by which factor do we blow up the matrix now? This is already a part of this nice scalability of this code. Yes, so we will see actually where the code rate will come into play, what you mean by security of the code. So right now, just thinking about different block sizes. Within the block size, we can then think which part of the block will be parity bits and which part of the block will be information bits. So also this will be nicely scalable. Okay, zero elements replaced by zero matrix. Now just the question is, what do we replace the non-zero elements with? So the 1 elements replaced did I call this here by cyclic permutation matrices. P Aj. So this permutation matrix depends then on the index of the row and column. So let's underline it. Actually, I wrote this as index here. Write this either as function or as index. Be consistent with the lecture slides, so write it as index. J. So it's the identity matrix. Shifted Pij times just now how often will the value be shifted, And this depends on the values in this table. So obviously, if I use here a lifting size of 4, and this number would tell me shift it 9 times, of course, you see this somehow circles. After the 4th shift, I will start at the beginning. So I need to think about how to get the number of shifts. And we can state here that Pij can be obtained from the table. Actually, Pj is like the modulus of the entry in the table, Vij, and then this lifting size. Entry in the table, here the so-called lifting size. So again, for our example of 3, of 4, let's illustrate this slightly different. So we have here ones here, 0 up and this just should illustrate here shifted versions. Cyclic shifted versions. Entity matrix. We can act result on sets. So here I used Basegraph 2, set 0, on specific configuration here, and this is already the matrix with zeros, where we have the zeros in the base graph, and ones being reflected by the black dots, where we have non-zero entries in the base graph. So the black ones here now will get replaced by identity matrices and circularly shifted versions of identity matrices. And if I do this for my example, you're looking about the numbers, it's like explaining how this is done. I also used here the size 4, shifted by 1, it's this guy. This operation. Here finally will end up with the parity check matrix. Here you actually recognize this 4x4 matrices. Can we also draw? Here, the first block 4x4 obviously is a cyclic shifted identity matrix of size 4, shifted by 1, defined by the number in this base graph. Second block here again shifted by 1. Then we have another block here, shifted by 0, so the identity matrix, and so on. So this is now the finally resulting first part of this parity check matrix containing the shifted versions of the identity matrix. If we do this for all, you see the matrix got bigger, blown up. You see here this parts of the 4x4 identity matrix and the shifted versions of it. And you also see here the last part, what you already commented, there we somehow see this identity matrix as last part of the parity check matrix. So this is one parity check matrix that could be generated from the definitions of the 5G standard. So there are many more, depending on what block size I would like to get. So here we have like 200 something. This would be the block length. And the first columns here, so the more dense populated columns, belong to the information bits. And this remaining part here belongs to the parity bits. So there we have a matrix quite with a strong protection, many parity bits for only like few information bits. Yes, so this is basically the final result, how to get parity check matrix from the standard G. Sorry, I didn't. Let's see, here's the question, if this was shifted by 4. Yes, we actually see this, that the lifting size of 4 was used here. Here. Actually, the dots not really display well here. It's more like scaling problem. But go back to this one here. Here, when we look at the numbers instead of the diagram, we actually see that here we have submatrices of size 4. Probably I've also written this in the slides before. Yes, here we actually used Z being 4, the lifting size. So we have 4 possible submatrices that can appear, identity matrix, and the 3 shifted versions of it. And now, of course, by selecting different lifting sizes, different Z indices, we get this whole flexibility of this 5G matrices. Yeah. Next time I will repeat again some things related to this. But for today, I think we are done with this example. Now you should be able actually to understand, at least to be able to do something with the definitions here from the standard, because of course, obviously, on the first spot, this looks somehow strange. But it is like this, that the codes are efficient to encode, to decode, that they avoid short cycles, and those are the main reasons why these numbers look as they are. Do you have questions related to this? Okay, so then we are done for today. I will see if I can come up with some more good explanations about these numbers. But for today, we have one question here. So could you once again explain why the girth was 4? Okay, so a question going back towards what we did before. Let's answer this one. So the question why the girth is 4. Yes, so here again, the girth basically describes the length of the shortest cycle that can appear in such a Tanner diagram. And of course, there cannot be a cycle of length 2 because we need at least 4 paths until we can get back to our original value. So the shortest cycle that can appear would be of length 4. Oh, hi, Mike. Would be of length 4. We can only have longer cycles. So the next length, possible length, would be a cycle of length 6. And well, the girth basically describes the smallest number there. So for better codes, the girth will be, for example, 6 or 8, for example. 4 is quite bad because already after the second iteration, we start to lose the independence of our additional information. Okay, so did this answer your question? Okay, so then I think we are done. Thank you for your attention and see you again next week.